Welcome to my YouTube channel Coulomb Academy. Friend, in this series of mechanical vibration numericals on the single degree of freedom, we are today taking the numerical on this free damped vibration with a single degree of freedom. This example I will read it. Machine mounted on the springs. There are number of springs are there and fitted with a dashboard has a mass of 60 kg. See, this is the 60 kg and there are 3 springs are there and each stiffness is 12 Newton per millimeter. The amplitude of vibration reduces due to this damper from 45 millimeter to 8 millimeter. That means this reduction of this one will be up to 8 millimeter in 2 complete oscillations, means from 1 point to this one oscillation and the second oscillation it will reduce the amplitude from x1 to x3. Okay, x1 to x3 from 45 to 48. So there are number of oscillations. These 2 complete oscillations are 2. Okay, so assuming that the damping force varies with the velocity, assuming this damping force varies with the velocity. So determine the damping coefficient C. We have to find out the ratio of frequencies damped and undamped. Means damp and undamped, this omega d by omega n. And also we have to find out the periodic time for the damped vibration, means TD. We have to find out. So friend, what is the given? M is given 60 kg, x1 45 and x3 3 oscillation. So x3 is given 1, this second and third, like this 3 oscillations are given. Oscillations are 2, but this x1, x2, x3 just were drawn, and the amplitude this x2 we don't know, but value of x1 and x3 are given to you 45 and 8. Okay, the number of springs, how many springs are there? 3 springs are there, with each spring having the stiffness is 12 Newton per millimeter. So we have to convert it into 12 into 10 to 3 Newton per meter. That is important. Okay, so why it is required to convert? Because this all the dimension we have to convert into one single unit. So next will be the what we have to find out. C, damping resistance. This ratio of this damped frequency to the natural frequency, and the time period we have to find out. So how to find out this one? So friend, you will see one by one. Here simple step, these are the given data. We have to find out the value of C. So how to find out the value of C? For this we require the value of zeta. The zeta we require, and also we require the value of, to find out the value delta. Delta value we can calculate that as a logarithmic decrement. This is the as a logarithmic decrement. Logarithmic decrement. This value we can find out by using this formula. That standard formula is for n number of cycles are there. Then this log of, this is the log of to the base e, this x1 by xn. So this n is the number of oscillations are there. So this n, this is the formula we have to find out by using this formula. Okay, value of del. This how much the value then? The total n we know. The total 2 oscillations are there. How many? In numerical already it is given to you. The 2 complete oscillations are it is given in the numerical. So I will write here itself 1 upon n is how much? 2. N is how much? Here number of oscillations are 2. The 2 minus 1 log to the base e. X1 is given 45. The value of x1 is given 45 and x3 is the last value. X1 and x3 are given to you 8 millimeter. So 45 by 8 So this value of del becomes right here 0.8636. So this value which will be beneficial to you to calculate the zeta. So how to find out this zeta? I will write here. Here zeta, this zeta we can find out by using this formula of this del upon under root of 4 pi square plus del square. This is the del. The same value we are calculated here. And put it this value in this equation, the 0.8636 divided by in denominator 4 pi square plus this del is the 0.86. Inside the bracket I will write 0.8636 square. So just extend the line. So this zeta I will get, this zeta, value of zeta is become right here 0.1362. correct? This is your value. Just find out. Now what we have to do? By using this zeta we can find out here the value of c. What we have to find out? The value of c we have to find out. So how we can find out? This zeta is equal to c by cc, or we can write the c by under root of km. This zeta we know. Here in this case zeta we have the value of zeta, but here the cc we have to find out. The cc we don't know, so we can find out cc by using this k and m. What is the value of k here? In this case, what is the given to you? Here, see, I will read it again. The 3 springs are given to you. They are mounted, the machine mounted on the springs. Number of springs are 3. So what do we have to find out then? Then k equivalent. The springs are in, suppose the springs are in, I will draw here figure. Springs are in parallel arrangement. The springs are in parallel arrangement. So what will happen in this parallel arrangement? The machine is mounted on the spring. This k1, all the values of k are same. So k equivalent we can find out by addition. In parallel we can do the addition. So k1 plus k2 plus k3. The value of this all spring is given 12. Okay. Each spring, the spring value stiffness is given. K1, K2, K3 are same. In this case 12. 12 plus 12 plus 12. So what is the value of Ke then? Then Ke equivalent spring stiffness is Ke equivalent spring stiffness become here you can write 36 into 10 raised to 3 Newton 10 raised to 3 Newton per meter. Once we got the value of Ke, what we have to find out? The Cc. Now we have to find out the C. How we can find out the C? Zeta we know, this value of zeta we know, and this K and M we know. K means what here? Ke equivalent. Okay, so C is equal to zeta into under root of Km. So putting these values we will get here. I will put the values of all the things. Twice is remaining, into 2 is remaining. So I will let here also 400. I will put the value after putting and just solving by using this calculator. We get the value Newton second per meter. This is the value for this C. What we have to find out? The first term we just calculated. Now we have to find out this, the ratio, this WD by WN. How can find out this WD? WD we can find out by using this WN. The WD is formula. By using this formula, WD is equal to Wn into under root of 1 minus zeta square. So this is the formula we have to utilize to calculate the value of WD, means damp frequency. What is this? Damp frequency. By using this damp frequency, this ratio we can find out WD by Wn. So this we have to find out, but we know this Wn is equal to under root of Ke by m. This is the natural frequency. The Ke we know, the value of Ke is 36 under root of 36 into 10 raised to 3. And what is the value of m? M is given in this numerical. The dashboard, this total machine mounted on this one, and is mass of 60 kg. It is mounted on this mass of 60 kg, and it is also written here mass of 60 kg. The kg. Okay. So omega n becomes, we get the value from the omega n. Here I will write this formula Km by m. So omega m become here 24.4968 radians per second. This is in radian per second. Friend, here what we have obtained? Wn. Okay, omega n, that natural frequency, and by using this, putting in this equation, we can find out the damp equation. So I will write the value of the damp frequency, this 24.49 inside the bracket 1 minus zeta. Zeta is how much? Already we have calculated value of zeta 0.1362 inside the bracket 0.1362 square. So just solving this, we will get the WD. So what is the value of WD here? We will get the value of WD here. This I will write directly near about this value become near about same 24.2665 radian per second. This is the value of WD, this is the value of Wn. What we have to find out here? We have to find out this ratio WD by Wn. So WD by Wn I will write here WD by Wn means damp frequency upon, well, it's asked in the ratio of the frequencies, damp and undamped vibrations. It is asked in this numerical itself, second point. Okay, so that we have to find out now. The second point, at 24.2665 upon 24.4968. So this ratio becomes how much? This ratio becomes of the frequencies is now right here. See, 0.9906. This is the ratio of this one value. Okay. Similarly, we can find out this periodic time. How we can find out the periodic time? This damp vibration, under this damp vibration, this periodic time we have to find out. That means the TD we have to find out. How to find out TD? TD you can find out by using the formula, simple formula, that is nothing but the 2 pi upon omega d. This is the formula we have to calculate the time period. So we know this value of omega d. Just putting this value here, 2 pi upon 24 by 24.2665. This is the omega d, and lastly we will get the time period. Here I will write the value 0.2589 second. So friend, this is the value for this time period is 2589. Means here I will write again value is 2589. Okay, in second. So this is the value for this time period for the damp frequency. So friends, so already I will read it, show you in short. This is the numerical on the free damp vibration. Is all the values are given to you. M, X, X3, X1 values are given to you. K is given to you. What we have to find out? This damping resistance and the ratio for the damping frequencies, damp to the natural frequency, and time period we have to find out. That's why I calculated these values. Zeta is the first value we have calculated. From this zeta, we calculated the value of C. Okay, this is the first value, and this ratio for this damp, that is your second value. Okay, and lastly, the time period we have calculated here is 0.2589 second. Okay, in second. So friend, please subscribe my channel for more and more video. Please subscribe my channel. Okay, thank you very much.
What are the outcomes of this video of mathematical modeling for this all the vibrating system? I have down 3 outcomes, and friend, here you always learn by self-assessment only, and you have to subscribe my channel Coulomb Academy. If you are not subscribed, please subscribe it. Thank you.